The opportunity I get to talk about shit and urine with a bunch of people I enjoy without people making a face. So yeah, my name is Temitope Ogunyoku. I'm from the University of California, Berkeley, and I'm doing my postdoctoral research there. And so today I'm going to be discussing the research that we've conducted over the past year. The title of my talk is The Disinfection of Latrine Fecal Sludge with Ammonia Naturally Present in Excreta. So first I want to discuss some issues with the sanitation value chain. So in developing countries, in some areas, waste is collected either through a pit latrine or a collection bin. As you can imagine, that, as most people know, that excreta possesses a high concentration of pathogens. So with these pathogens, they are throughout our entire sanitation value chain. So when a pit latrine gets full or a collection bin gets full, it needs to be emptied. So you have different options of emptying. You have from manual emptying to mechanical emptying. Manual emptying is the cheapest way of emptying a pit latrine once it's full, but as you can imagine, it's the least hygienic option. And there's a whole bunch of high risk associated with manual emptying. You have the mechanical emptying with the vacuum trucks, which is great if you actually have the money to empty your pit that way, and also if you have the space. In most, especially in urbanized areas in developing countries and lack of infrastructure, these vacuum trucks cannot get through the area to actually vacuum up the waste. Then you also have the transportation. If the waste gets treated, and if, that's a big if, because in some situations the waste just gets thrown into a lagoon or into the open source area. If it does get treated, these common treatment systems does not adequately treat all pathogens. And if the waste is being reused or if it's disposed in the environment, people are still exposed to pathogens. So the objective of our research is, let's treat the waste at the collection point. So treat excreta at the point of collection by harnessing ammonium that's naturally present within our own waste. Once we treat the waste here, all the subsequent processes such as emptying, transportation, and further treatment, it's safer because the waste has been treated at the collection point. So here's our safe sludge disinfection approach. You have urine, which contains urea in it. And you have feces, which has the enzyme urease. So when combined together, ammonium, NH4+, is produced. By adding an alkalizing agent, you increase the pH and therefore convert ammonium into ammonia, which is a powerful disinfectant, which was just discussed, that is known to kill all types of pathogens from bacteria all the way to helminth eggs. So here are some of our research questions. What form of urease is best to actually convert urea into ammonium? So urease from jack beans, which is urease is processed in a chemical company, or is urease from feces sufficient enough to actually convert it to ammonium? And then what alkalizing agent is best to actually convert the NH4+ to ammonia? So you have quicklime, limestone, biochar, ash, or lime. And so ammonium, the acid dissociation constant for ammonium is 9.3. So at a pH of 9.3, you have 50% conversion of NH4+ to NH3. So if you can have an alkalizing agent that is strong enough to convert, to surpass the 9.3, you can get a lot of conversion from NH4+ to NH3. Here are some of our other research questions. What are the activation rates of pathogen indicator organisms using our safe sludge disinfection process? And how can we incorporate this safe sludge process into toilets? So here are some of the experiments that we've done. Thanks to the wonderful graduate students at Berkeley, I've been able to actually collect real feces and urines to conduct my experiments. So 4 to 6 individual urine samples were collected and mixed. Once we mixed the urine samples, we added calcium hydroxide to obtain a pH of 8 to 12. Now, so this is to determine the hydrolysis rate of urea. So I did one set of experiments without any urease, one with urease from jack bean and one with urease from feces. I took duplicate samples and measured ammonia and pH at 8 different time points. So here are the results. For pure urine, the native samples, meaning ones without any calcium hydroxide, pH increased over time. Where for the samples that contained the calcium hydroxide, the pH decreased over time. So I wasn't able to maintain a stable pH from 8 to 11. For the native and the pH 8 through 9 samples, hydrolysis did occur and ammonia production was produced over the 33-day period. What was interesting to note, at pH 10 and 11, the activity reduced conversion, so I didn't produce as much ammonia at pH 10 and 11. So here's the results for urease with jack bean. So again, I did this set of experiments from pH 9 to 12. Again, 9 and 12, through 9 through 11, the pH started to decrease. But we maintained a pH of 12 by adding about 2% calcium hydroxide. So throughout the experiment, 2% by weight of calcium hydroxide was able to maintain a pH of 12. The lower pH samples, though, hydrolysis did occur, but from pH 10 through 12, the hydrolysis of urea decreased substantially. So as you can see, urease is essential to actually get great hydrolysis. Okay, so here are the implications for the urine and the jack bean. The urease is needed to convert urea to ammonia. Urease from jack bean was not active at pH of 12, and it's necessary to raise the pH to 12 to actually maintain a stable alkaline environment. So the urease from jack bean, I'm going to compare it to the urease from feces. So the urease from feces, again, we were able to maintain a pH of 12, but the urease from feces was actually just as effective than the urease from jack bean to actually have hydrolysis. So natural urease in feces is the best source. It's confirmed again that a pH of 12 is necessary to maintain a stable environment. So what this taught us is that there's a two-stage process in order to create ammonia. You need first the urine and feces to be in contact for a certain period of time in order to actually create hydrolysis or create ammonia. And once that occurs, then you can add your alkalizing agent to convert NH4+ to NH3. So we did this at different ratios to determine if you would get more ammonia if you have more urine within your collection bin. So these are 3 different scenarios. So the 1.3 to 1 ratio, that's urine to feces, is a situation where every time everybody defecates, or majority of the time, that they actually release a little bit of urine. So the 1.3 to 1 ratio is that scenario. The 2.6 to 1 ratio is where a woman has a toilet within her household and is able to use the restroom more, and she's able to urinate, so you get a little bit more urine. The 5.2 to 1 ratio is if you have a party at your house and you're celebrating and people have a little to drink, and so you have more urine within your system. As you can see, so at this experiment, it's at ideal conditions of a pH of 7.2, where previous research has shown at that pH urease is most active. It's at 7.2, the temperature is at 37 degrees in a closed system. So the total ammonia, as your urine increases, you have more urea, so you're going to get a higher concentration of ammonia. And another confirmation is that the pure urine, which was spiked with urease from jack bean, compared to the urine from feces, the 5.2 to 1, produced about the same amount of ammonia. So that reconfirms that urease from feces is a good source. Now, which alkalizing agent was the best? As I previously mentioned, the pKa value for ammonia is 9.3. So here are the different alkalizing agents that we use. We use limestones at different sizes, biochar, ash, and calcium hydroxide. As you can see, in an aqueous environment, calcium hydroxide gave us the highest pH of 12.7, which would get you 99.9 conversion of ammonium into ammonia. So for right now, we figure it's most effective to use calcium hydroxide as our alkalizing agent. So here are the inactivation rate experiments of the pathogens, of the pathogen indicators. So we decided to do this experiment at 2 different ratios, the 1.3 to 2.6 ratios, and we spiked the MS2 cauliflage and incubated our samples for 24 hours at a closed system. The slurries were split in half, and then one portion of the slurry was amended with the calcium hydroxide. And duplicate samples were analyzed for E. coli total coliform and MS2 total ammonia and pH at 6 time points. So here are the results. This is for the samples that were treated with our Safe Sludge process versus our control, which were untreated. As you can see, the log inactivation was very quick. Within 4 to 6 hours, we were below the detection limit, which is the open circles, which is the open symbols, using our Safe Sludge method for the bacteria and viruses. And for our controls, we didn't, it took up to 2 or several days to actually get about 2 log reduction. And this is for a higher concentration, a higher volume of urine. Again, the same thing, we had greater than 3 log reduction for viruses and bacteria within a few hours. And for our controls, it took up to a couple of days to actually reach greater than 3 log reduction of bacteria and viruses. So the Safe Sludge disinfection process inactivated pathogens at a faster rate than our controls. And after 1 day of Safe Sludge process, can achieve greater than 3 log removal of E. coli and MS2. So how do we incorporate our Safe Sludge treatment into an actual toilet design? So what we did is that we gathered a group of volunteers ranging from students to architects, engineers, to help us develop a toilet that incorporates our Safe Sludge process. Again, we did 2 steps. The design requirements is that this was a 2-stage process where you need urine and feces to be in contact for a certain period of time, and then you add your alkalizing agent to create ammonia. And then the other requirement is that we ask for that it doesn't run on water or electricity. So we met several times to actually put together and design this toilet, and this is what we came up with. It's called our FreeLube toilet, Pathogen Free Toilet. So this design is designed for a family of 5. It's a service delivery model where it would be incorporated into a system where you would have sanitation workers come and empty your container once it's full and treated. So the stage 1 is where you have your hydrolysis of urea into ammonia. So you have an auger, so every time the person uses the restroom, they turn the auger where you have mixing, and you have the contact time of the feces and urine. So ammonium NH4+ is being created in this cylinder. After the 2-hour period, the feces slurry is dumped into the second container where ammonium production is occurring. So in this container, you have your alkalizing agent, the calcium hydroxide. And once the slurry gets dropped into the container, ammonia is produced right away, and then you have your inactivation occurring within the second compartment. So, one thing to note, we were able to present that toilet at the Reinvent the Toilet Fair this past August at the Bill and Melinda Gates Foundation. And so that was a very helpful conference for us to attend because we got valuable feedback of how to improve our design. And we're also able to develop a partnership with this group called SaNRG, who's located in Nairobi, Kenya. So they're a sanitation service delivery model in Nairobi, Kenya that have shared toilets where they hire entrepreneurs to manage the toilets, and they come and swap out the containers, the waste, where it gets sent back to a processing site. So we want to help them, or we want to partner up to include treatment at the collection rather than treatment at the very end of disposal. So I will be traveling to Nairobi next week to actually test out our Safe Sludge process over there. It's one thing to have experiments done in a laboratory where you have things that are controlled and things that are not necessarily clean, but I'm able to measure out the exact amount of feces and urine I want to produce experiments. Some of the challenges that we're going to have to face in Nairobi is toilet paper, sawdust that's added to the container, and also how closed or how sealed does it need to be in order to really create the disinfection so that the ammonia won't volatilize. So I'll be doing those experiments starting next week, and we hope to actually retrofit a toilet to incorporate our Safe Sludge process. And here are our future goals. So we did this over the course of the year with the experimental processes in the lab. So our future goal is to further develop the FSM2 toilet, to actually have them as household toilets that people can use. The next thing we want to do is to see if we can adapt this FSM2 to shared toilets, so the toilets in Nairobi, Kenya. And another thing that we know that is an issue is that there are thousands of existing pit latrines that are still in use and that would need to be pumped once it's full. So we want to develop a chemical additive to add to these existing pit latrines that would treat the waste within the pit latrines before it's actually pumped out. So through iterative design, testing and manufacturing, and also with monitoring the performance in Nairobi, we hope to develop a micro-enterprise social model. And based on this, make some recommendations and try to scale up. So we'd like to acknowledge the Bill and Melinda Gates Foundation. They're the ones that funded our project. UC Berkeley, my PI Carr Nelson, who's in the back, along with some undergraduate and graduate students who helped me along with this research, and Fake Design in Oakland, California.